Hello everyone, welcome to the webinar series with the IEEE Industrial Electronics Society. Thank you for joining. Today's topic is separation of the charge transfers and SEI contribution by modeling the non-linearities regarding current and temperature. And it's being presented by Dr. Nicolas Damay from the University of Technology of Compiègne in France.
Thank you, Cécile, and hello everyone. I'm very pleased to be here with you for presenting our recent work on that subject, which is separating two important contributions to the battery voltage, namely the charge transfers and the SEI. And I will detail all of these terms later. So I will be first introducing myself. So I'm Nicolas Damay. I'm assistant professor in France at the Université de Technologie de Compiègne. So I wanted to place our team on the world map. So we're here. So we are in engineering school, and we are also researchers from a lab, a kind of electrical engineering lab coupled with a mechanical engineering team. Our specifically battery team is focused on developing semi-physical equivalent circuit models for batteries. And we have, as a constraint, we have the user or integrator point of view. That is to say that we have no prior knowledge of the cell that we are studying, and we have to find everything from scratch. And also we exclusively use non-invasive approaches to do so. Our goal, or the goal of our methods, are the diagnosis, the prognostic. Also, for the batteries, of course. Also, we are building estimators for state of charge, state of health, and our model and methods can be used as design support tools for building battery packs or cells. We also work in collaborations with manufacturers, so cars manufacturers, planes, aircraft, trains, battery packs manufacturers, and also cells manufacturers. So today I will speak a lot about determining a battery state of health. So it is about a diagnosis. As you may know, battery capacity evolution during the life of a battery is extensively studied, and it decreases with the use of the battery, and also when the battery is just stored and not used. And there is also the increase of the impedance of the battery, and this particular stuff is important for power applications, and also like we will be talking in here about the understanding of what happened with the battery and how it has been degraded during its life. I wanted to bring one specific scientific law here, which is separating the contributions to the cell impedance. Separating them means that we may track some degradations of the electrolyte, negative electrode or positive electrode, or even more accurate things, or collectors, etc. In here, we will not talk about everything because we have no time for that. I wanted to start with an Nyquist plot of the impedance spectra of LFP graphite cells. It was quite old work, but we were interested by the evolution, in particular, of this part of the impedance. You got the pristine cell in here, which has here a small semicircle. This semicircle is related to fast dynamics and to given phenomena that I will detail after. And this particular semicircle here for an older cell tends to increase, and sometimes it increases a lot. And so it increases a lot the impedance, and it reduces the power that is available for the battery. So about the other part of the impedance spectrum, we have here an equivalent series resistance, which is called RS here. We can see strong variations. The strongest variations are here. It may vary, but not a lot. And also we have the diffusion part, which is the line here. And based only on the Nyquist plot, it's quite uncertain to determine if it has vary a lot or not. And so we were sure for a long time now that we may find a lot of information in the evolution of this semi-cycle, but there are a lot of phenomena that are mixed inside it, and so it makes it harder to understand. So I will be focusing my talk about all that may happen here and how to determine it. So a little bit of physics to start with. So we'll be talking about insertion batteries. That is to say, not only lithium-ion, but also all batteries that are based on the insertion principle. So there are also sodium-ion batteries and other technologies. They all work on the same principle, which is the rocking chair principle. A rocking chair is for the ions that are flowing back and forth from one electrode to another. And so during the charge, the lithium ions or sodium ions are flowing through to the negative electrode, and they are inserted inside the materials. For being inserted, they have to be combined with an electron that is coming from an external circuit. And this combination is called the charge transfer reaction. It occurs at both electrodes, and it allows the ions to enter the material, and it becomes electrically neutral. Well, when they are entered into the materials, they then are submitted to diffusion phenomena, and they can create concentration gradients inside the active materials on both sides. There are also concentration gradients in electrolyte. And finally, there are also the migration phenomena, that is the move of the charges due to electric fields. And so it can occur in the electrolyte, in the SEI, so the solid electrolyte interface that I will describe in the next slide. And also the electrons flow into the collector and active materials. All these phenomena will be responsible for some electrical potential variation and evolution of the battery voltage. And so if we want to detect one particular phenomenon, we have to extract its contributions from the main battery voltage. So let's focus on the charge transfers and the passivation layers. So here is another representation of a battery. We have the current collectors on the sides here, which bring the electrons to the active materials here for the negative electrode and the positive electrode. And we have a separator here. And everything is flooded in electrolyte in green. So we have an assembly of active materials particles. And if we take one particle in blue here, we can see that it is covered with a layer here in gray, a passivation layer, which is called the SEI. And so this layer is particularly important for the insertion batteries because it protects the electrodes from reacting with the electrolyte. But if it protects, it has also to allow the ions to get through it. So the ions can come from the electrolyte, cross the SEI here. So it will be related to some voltage drops. And in here I've represented it, this voltage drop by a resistance, RSEI. And then the ions are coming close to the active materials where they can be combined with an electron to enter the material. And in here, when there is this charge transfer reaction, there is another voltage drop, and it is also represented by an equivalent charge transfer resistance. This SEI if it's formed at the beginning of the battery life, it is also growing. It continues to grow during the whole battery life. And so it is interesting to track this SEI growth, because it consumes some ions to grow, and it will decrease the capacity and also increase this resistive contribution. Just a note about the positive electrode: we may also have a passivation layer on this positive electrode, but it's quite different from the SEI, and often it can be neglected, except for some cathodes that are the nickel-rich cathodes and the high voltage cobalt oxide cathodes. So here we will be focusing on batteries and cells that are only that have only 3 processes in here, so 2 charge transfers on the negative and the positive electrodes, and also a passivation layer at the negative electrode, so namely the SEI. But all these processes are combined into one only apparent surface resistance, and we will focus our study on these particular parameters. So this surface resistance RSUF corresponds to the semicircle diameter in here that is increasing a lot during the battery life. So a little sum up, little assessment, where the main idea is that the impedance increase during the battery life, and it's critical for power application. The increase of the charge transfer and SEI contributions may bring, we believe, that it may bring valuable informations on the state of health of the cell. And finally, I remind you the scientific clock in here. That is, these phenomena are mixed together into a single apparent resistance, which is called the surface resistance. And as we saw earlier on the impedance spectrum, you cannot easily separate it with only this semicircle. So the working approach and also the plan of this presentation is based on these four bullet points. First, I will show you how to model the nonlinear behaviors of the charge transfer and the SEI regarding two things, the current and the temperature. And the aim is to bring a physical model for this surface resistance. After that, we will go into the experimental characterization of this surface resistance for different current and temperatures. Then, by fitting the data to the model, I will show you that we are able to separate these charge transfers and the SEI. And finally, we will have some applications to different cells to track the degradation of the charge transfers and the SEI. So let's jump into it. The model. Oh, I've already talked about the physics. So in here we'll be focusing in a first part on the charge transfer. The charge transfer is related to one well-known equation, which is the Butler-Volmer equation that you have here in green. And so with this equation, we may compute the current that is flowing through some interfaces, thanks to a parameter here, which is the exchange current, and two terms that represents the insertion and the deinsertion of the ions. And they are competing with one another, and it depends on the sign of the over voltage, VCT, depends on the sign of the charge transfer over potential. They might be sometimes symmetrical or non-symmetrical, but for quite a lot of batteries, there is an assumption which is made, which is that this charge transfer coefficient that you may find here and here is symmetrical, and so is equal to 1/2. And then you have physical constants, the Faraday's constant, the ideal gas constant, and also the temperature, of course, which is very important for chemical and electrochemical reactions. I have represented the behavior of the Butler-Volmer equations as characteristics here. So we have the voltage, the over voltage, and the current. And so for when the over voltage is increased, the current may at first start to increase slowly, and then it may increase a lot faster when the over potential increase. because it is an exponential behavior. And if it's symmetrical, like in here, we have exactly the same behavior for positive overvoltage and negative overvoltage. So that is it for the non-linearities of the charge transfer regarding current. And then for the SEI contribution, in most of the literature, we found that it could be assumed to be linear. That is, that the overvoltage due to, or the voltage drop due to SEI is related to a resistive behavior. So on the characteristics that would lead to a stroke like this. Because maybe, and because we are from an electrical engineering lab, we like to see the phenomena as equivalent resistances. So in here, I will show you how to transform this Butler-Volmer equation into an equivalent resistance in here. So if we have this symmetry coefficient here equals to 1/2, the Butler-Volmer equation can be rewritten with a hyperbolic sinus. And so we still have the Faraday constant and everything and the overvoltage drop. What we want here is to, instead of computing the current as a function of the voltage, the overvoltage, we want the contrary. So we want the overvoltage as a function of the current, because it is more convenient to express the charge transfer resistance in here. So we will just divide this overvoltage by the current to have something that is equivalent to a resistance. And so you have here the equivalence to Butler-Volmer phenomena or equation at the resistance. So I just described it on the figure in here. So for small charge transfer over voltages, we have a strong resistance, and then as the overvoltage increases, we have a decrease of the resistance. Because some of you may be more familiar with this formulation of the charge transfer resistance, I wanted to show the consistency of this model with it. So the classical RCT formulation is often determined or related to EIS, so the impedance spectrum measurement, that is for a current that tends to 0. So here, when the current tends towards 0, we have this behavior that is remaining. So we have the classical formulation for charge transfer resistance around for near zero current, which is RT divided by the Faraday constant and the exchange current. So we have here the Butler-Volmer behavior at the resistance, or at an equivalent nonlinear resistance in purple in here. And if we want to integrate the SEI behavior, which is only a resistive contribution, it leads to a translation, a pure translation of this curve. And so we have here the model for the nonlinearities regarding current only. And then I will be discussing about the nonlinearities regarding temperature. We've done a lot of research into the literature, and we found that the exchange current is activated by temperature, and so it will be answering to the Arrhenius law, and also the resistive contribution of the SEI, RSEI, is also answering to the Arrhenius law. So you may have seen already this law that has been described for a reaction rate. Okay, so we have this formula, but in here we wanted to use a more convenient form of this equation. It is basically normalized around the 25 degrees Celsius. So we have here a little modified term for temperature, and in front of the exponential, so we have the value of the parameter, but at 25 degrees Celsius. So this one is a parameter that can be fitted, and this one, the activation energy, correspond to the strength the strength of the thermal activation of the process. That is to say, if we have a high activation energy, the process will be depending strongly on the temperature. And if we have a small activation energy, the process will not be impacted a lot by the temperature. And finally, you have here the Boltzmann constant. Sorry, a bit of water. So that is the expression that we have for the exchange current, and then we have the same kind of expression for the SEI resistance here, with a pre-exponential term, which is a parameter 25 degrees Celsius, and an activation energy. But I wanted just for visualization to show you an example of the Butler-Volmer characteristic for different temperatures. This is a simulated curves for classical parameters that we found for our batteries. So you have the the Butler-Volmer curve for 25 degrees Celsius in here, which is almost linear. Almost linear, it means that it is close to purely resistive behavior. And when the temperature is decreasing, we have a more curved behavior, like in here. And so we will have a strong non-linear behavior and a strong and a resistance, equivalent resistance that depends a lot on the current. So to sum up, we have here the complete surface resistance RSURF model. We have included the non-linearities regarding current and temperature. So we have a surface resistance that depends on both these values, with RCT and SEI. This expression that depends on current, and these two terms in here that depends on the temperatures, both of them responding to this modified Arrhenius laws. So the final equation is might seem a bit complex, but at the end we only have 4 physical parameters to determine, so it's quite easy to do with an optimization process, an optimization algorithm. We have two parameters at 25 degrees for the SEI resistance and the exchange current. So I want to remind that from the exchange current we can compute a charge transfer resistance. And we also have 2 activation energies. So now I will go to the experimental part. So how do we extract this surface resistance from the battery itself? This is done in 2 steps. The first step here is based on the impedance spectra measurements. So we have to put the cell in a climatic chamber to control its temperature. And then we do the classical EIS for electrochemical impedance spectroscopy at the desired state of charge temperatures. And we may have results like this one with a very small impedance in here for high temperatures, like 45 degrees in here. And then when the temperature decreases, this semicircle is increasing a lot. It is doubled, tripled, multiplied by 10, very large increase. And we can also, from this impedance measurement, determine the equivalent series resistance, which is not which is needed for we need its value just to separate the surface resistance from its contribution in here. It's just that we need its knowledge for a good separation of the surface phenomena contribution. And from this impedance spectra, so we may found this point, the point that is near zero current in here. So just the top of the bell curve. After that, we need to determine the other points in here. So we cannot use the impedance spectrum because they have to be done for small currents. And so for the second step of the characterization, we will use current pulses measurement, and we do them at the same sock, the same state of charge, sorry, for different currents and different temperatures. And so you have an example of a voltage response in here. And to extract the surface resistance from this response, we use an equivalent circuit model here. So we fit it to the data. It's a quite classical ECM. It renders close to a renders circuit, which has an equivalent series resistance for in here the initial drop, which is quite small, and because it is quite small, we use the equivalent series resistance that we just found in the impedance measurement in here. And then, so this one is fixed, and we have to we let the an optimization algorithm fit and try to find the best surface resistance, the best time constant in here, and the best diffusion representation in here. So for the diffusion, I didn't brought the details in here, but it's modeled by a classical lens impedance, like it's done in many studies. So this modeling of the diffusion part is only required to separate the different dynamics in here. And so with that, we can find the different results for all the operating points of the battery, and we verified that the surface resistance that we found here for quite small currents are quite consistent with the impedance measurement in here, and it was okay. So now I will show you the results on our real batteries, starting with some LFP graphite cells. So here is what we've done. So we have the surface resistance values that has been determined thanks to current pulses and EIS, and it has been done for several currents and several temperatures. So as you may see, there is a very good agreement between these the model and the data. We have here for low temperature, we have a very bell-shaped, which is quite narrow. In here, a bell shape for the Butler-Volmer behavior. We have in here, we can see that it do not tend toward zero, because here we have certainly SEI resistance that is remaining. And when the temperature is increasing, we have a strong decrease of the resistance. So we have a very strongly thermally activated process. So we expect high activation energies, and in the end, as you may see on the zoom here, we have quite nearly constant values for temperature, for room temperature and higher temperature. So what did we find in here? We have the values at 25 degrees for the SEI resistance, so which is 0.47 milliohm. We have the exchange current. So I did the calculation because it's more convenient to compare with the results in here for the charge transfer resistance near zero amp, so which is 0.79 milliohm. And also we have the activation energies in here, so 0.6 and 0.8. Please note something. It is that we only have one Butler-Volmer equation in here. It means that we only represent one charge transfer process, and so it implies that it might be one of the negative electrode or the positive electrode, but it implies that one of the two processes, one of the two charge transfers processes should be negligible. If it wasn't, we would require two Butler-Volmer equations and two charge transfer resistance to model our cell. And finally, we verified that the activation energies that we found are consistent with the literature data, and they were. So you may find more information about these results on an article that we've published in the Journal of Power Sources. When the model is fitted, so we may have the behavior of the estimated behavior of the SEI on the one hand, and also the estimated behavior of the charge transfer on the other side. So I wrote them in here. with dotted lines for the charge transfer and classical lines for the SEI. So you have all the temperatures and the different processes. If we look only at the low temperature behaviors, we have still a strong bell-shaped curve for RCT, and we can see that this charge transfer is very dominant for small currents. Near zero current, we have very strong influence of the charge transfer, and then when the current is increasing, this charge transfer resistance is tending toward zero, and so it remains the only thing that remains is the SEI resistance in here, which becomes dominant for high currents. So it means that they are quite easy to separate when the cell is operating at low temperature. At a higher temperature, we have a quasi-linear charge transfer resistance and SEI resistance, so it's quite impossible to separate them. So I want to bring here some perspectives for the use of this method for the battery management system, the BMS. When the battery is operating at low temperature, so for instance in winter, it seems possible, maybe, to recalibrate the surface resistance model online. And if so, if we can recalibrate this model, the SEI growth might be tracked as well as the charge transfer resistance increase. So here are some ideas about an eventual online recalibration. I've used data that I had on the same battery, which was used on an EDC profile. So it's for new European driving cycle. So it's a driving profile. It will not be used in a few time, but it's not the point. The point is that several operating points are met during the driving cycle of a car. So we have different currents. I reported some values in here, and I have also reported these values on these graphs. So we can see that during the normal operation of a battery, we are crossing different operating points, and maybe if we are able from the voltage measurement of the battery to extract the surface resistance, maybe we can recalibrate the model. And the one question is which temperature is sufficient to do so? We may ask ourselves this question. Maybe we can see the green curves are still a little bell-shaped, so maybe it's possible. It's better to do so for very low temperature. So it's better to live in a cold country. So now I will show, this was some perspective for the use in a BMS, so for a real application, a commercial application. We've done also some tests in our lab, so in lab conditions, for the determination of the state of health of some batteries using this model, using this approach. So here the study has been made on the aged NMC plus NCA cells for the positive electrode. This is a blend, and for the negative electrode we have a blend of graphite and silicium oxide. This has been done with through a project with an aircraft manufacturer, which is called Safran. The project is to for the airplane operation. Of course, we require the highest reliability for batteries, and so it is quite interesting to be able to recalibrate the model during the battery lifetime. So here we've done some study about that. We have conducted the test on Samsung cells on 18650. And we had 3 different cells, one pristine cells, so with a 100% state of health. Another cell which has experienced cycling and also calendar aging. So calendar aging is the battery is just stored and it ages without doing anything, and it brought this cell to a state of health of 95%. It means that it lost 5% of its capacity. And finally, a third cell, the C cell, which has experienced only calendar aging in quite extreme conditions, namely 60 degrees Celsius and 100% state of charge. So it has lost 13% of its capacity. The conditions here are a bit harsh, but so it may be quite different from an application, but it is interesting here for the modeling purpose to see if we still can model the behavior of this kind of cell, this highly damaged cell. So for the study, we also made the characterization by EIS, the measurement of the impedance spectra, and short pulses, so 20-second long current pulses, a different current. So here are the results. We have the results for the pristine cell. Here, for the cell which has lost 5% of its capacity, and the most degraded cell here. First of all, we were quite satisfied that the model could represent so well the data. We have a very good agreement between the model and the data. And then we looked more closely to the parameters to see if it has a real physical meaning. And we were satisfied to see that the activation energies found in these three situations were nearly constant. It means these activation energies are related really to the processes, the insertion processes, and this insertion process should not be changed by aging, at least not locally. They may be changed at the system scale, but not at the local scale. And these activation energies should be how to say? These activation energies should be related to these local behaviors. So these parameters not changing means that we are close to have a real physical parameter. And so now that we were confident with these results, we considered it as efficient to diagnose the cell, so to extract the behavior, the state of the SEI resistance, and so also the state of the charge transfer resistance. So for the results, from just observing the curves in here, we can see that the surface resistance is increasing, and I've shown the increase in here. So we have some increase in here, and this is the surface resistance is what we can see only from the EIS, so from the impedance spectrum. With our model, we can separate the SEI contribution and charge transfer, and so we can see what is the increase of the SEI and of the charge transfer. And we were quite surprised to see that if the SEI is almost multiplied by 2 in this case, it is also multiplied by 5.6 for the charge transfer resistance. So we were quite surprised by these results, and for now we have not yet interpreted why there has been so much degradation on these particular parameters. About this work, it is currently presented today in Nancy at an international conference at Electromax. So here you have a work that has been done by a PhD student, Fernanda Van Ram, and the papers will be soon available online, I think. So this about the state of phase evaluation, we find this result interesting, and so what we want what we can state is that for the online recalibration of the model, we might consider the activation energies as constant. It means that only two parameters has to be changed to recalibrate the model, and we can represent this complex behavior in here by only changing these two resistances. So only two parameters might might be possible for BMS to do. So of course it would have to be verified for other technologies. Here we may track the SEI resistant growth. So we know from literature that the growth of the SEI is related to a consumption of lithium ions. So if the SEI grow, it means that the capacity should be decreasing, and on a theoretical basis, these two phenomena should be related and correlated. And finally, the track of the charge transfer resistance may be quite interesting. This is the main reason for the surface resistance increase for these cells, and this should be caused by a degradation of the active material interface, and maybe a loss of active surfaces. And I found in the literature some relationship between the capacity decrease that sometimes accelerates for the batteries, and also when there is some acceleration of the capacity fade, there is also an increase of the resistance of the cell. So maybe when there are too many active surfaces that are lost, we have some passivation of active materials. So there might be a relationship with the knee, this knee here, in capacity fade trajectory. So this is all for this application to the state of health determination. And lastly, I want to show you some application of this model, of this approach, to another technology of batteries, which is the sodium-ion batteries. So sodium-ion batteries, they are working on the same principle that lithium-ion batteries, and this one in particular are made of NVPF for the positive electrodes and hard carbon for the negative electrode. So we have a particular behavior in here. We have a plateau region here in which the sodium ions are inserted inside classical graphite in the hard carbon negative electrodes. And we know also that in this part, the sodium ions are inserted into disordered carbons. So they are inserted, adsorbed by pores and defects. And so the insertion or adsorption behavior should be different from this one. So we wanted to test our approach, and we can see also on the impedance spectra that for the zone A, in green is here, we have a smaller surface resistance, and when the state of charge is decreasing and we are going more to this behavior, we have a very strong increase of the surface resistance. So we want to see if we can understand if what are the modification, if the model that we propose here is still relevant. So we started with a test of the model for high state of charge, so in the plateau region, and we were happy to see that it fits perfectly the data. So we found here activation energies that are quite close to the one that we found for other lithium-ion technologies. So about 0.4 electron volt here for the SEI, and 1.9 electron volt for the exchange current. So in here we have a classical behavior. So we still can use the model for diagnosis purpose, at least in this region. This work is also being presented today in the same conference in Nancy, France, by our PhD student Hussam Rabab. And for the low state of charge, we had some difficulties because the behavior is very different. You can see from the magnitude here that we are around 300 milliohms, and here we are like 10 times higher. So we have a very strong increase in the surface resistance, and also you may see here that it is a bit less. It is less symmetrical. So we have a little shift of the curve to the discharge part. So it means that the ions are more easily de-inserted from the hard carbon than they are inserted in the hard carbon. It's a oh no, sorry, it's the contrary. It's a little harder to, the resistance is higher for extracting the ions from hard carbon than from inserted the ions to the hard carbon. So we have a charge transfer that is no longer symmetrical, so it complicates a bit the approach, because we have to modify this beta, this charge transfer coefficient in the Butler-Volmer equation, but it's still possible. And the activation energies here remain in the same range as before, so it's around 0.4 or 0.5 electron volts for the SEI, and around 0.9 electron volts for the charge transfer. So we can still use this approach, but in here, as we have a little different physical behavior in here, we have to take into account some asymmetrical behavior. So that will conclude my presentation, and I want to acknowledge some people who have worked hard for bringing all these results. So main contributors for these works are myself, Nicolas Damay, Karik Mergo-Mbeya, who was a PhD student and is now a doctor, Christophe Forger, who are professor in our team, Fernanda Vandram, who is a PhD student, Hussam Rabab, also a PhD student, and Guy Friedrich, who is a professor in our team. So you have here the three main publications about this work. So the initial model development, which is already available in the Journal of Power Sources, and also the two applications for state of charge tracking, and also for the applications to sodium-ion batteries from Fernanda Vandram and Hussam Rabab. So we have all these publications on ResearchGate, and you can feel free to contact me for the recording of this presentation, or the presentation itself. You have my email in here, and thank you.